Hello YouTube, this is a video response for Mark and Frank about the Don Smith device. I finally got a chance to, be home. I travel a lot, to replicate this circuit in the way that I think that it should go. Just so you know what my background is, I'm an electrical engineer, design engineer for automation. I design. Somebody wants something automated, they ask, and I do it for them. So anyway, once in a while I get a request for something like this over Unity device, and I'm actually I dabble, but so I'll explain the circuit. In the background there you can see there's the rotoverter experiment somebody wanted me to do, so I got a couple of junk motors and set that up per the internet. And of course it doesn't work, not even close, but that's another video. Anyway, so Mark and Frank, I know there was some texting back and forth and some confusion on this, and I noticed that Mark, you haven't posted another video on this, and I'm guessing you've figured out that there's a problem with this. So anyway, this is the schematic right here, and we're going to go over that, and we'll go over this schematic versus my schematic. And I wanted to look at some of these formulas. For instance, this one right here, he says T equals frequency in cycles per seconds. That is wrong. T does not equal frequency. T equals time, and time is, and frequency is actually 1 over T, and time is 1 over F, 1 over frequency. So anyone who owns an oscilloscope knows that. So that bothers me. You could tell through this whole video I'm kind of not happy about this schematic, mostly because, you know, Don, you know, he's no longer around, and he left us this vague idea is all you got right here. This is just an idea. None of this works. None of this. It says that this resistor here is to set the pulse rate of your NST, which is, you know, this guy here. No, that does not work. That is not how that works at all. What this resistor will do is limit your voltage. It has nothing to do with frequency. Now the capacitor here, if you put a capacitor in parallel with this NST, it shorts it out and it turns off. So that does not work. Now let's assume Don is trying to find the resonance of this portion of the circuit, the coil inside here, the frequency, and the capacitor. If you put the proper capacitor in parallel here, never mind the resistor, this becomes an open. What happens in an open? Well, the NST shuts off because it senses an open. It doesn't work. So if you had one of the old school NSTs, which is like a giant brick, which is literally 2 coils, your standard transformer, step-up transformer, then it won't shut off. However, you will short it out and you'll burn it open. And if you put the proper capacitor in there, let's say, to find the resonance at 60 Hertz, because that's all they're going to put out, then you have an open there, and it changes the scenario actually, that you may be able to draw something off of this. So either Don had one of those old style NSTs, which I don't have to point out. I had one, but I burned it open and I threw it away. If he was using one of those, then this changes some things, so not a lot. But then, of course, you know, he's going to have an inverter in here too. The other thing that is interesting about this is, you know, he puts this diode over here and a varistor right here, which this varistor is going to do the same thing that this resistor does here. It's going to limit the voltage. So what happens is, if you put a resistor across this capacitor, you're only going to allow this capacitor to build up X amount of charge, because the rest of it just gets drained across here. So of course the higher the value of this resistor, the more this capacitor is allowed to charge up. Because if you imagine this was just a wire right here, then basically the capacitor never charges because you got a short, right? And as the resistance gets higher, you allow whatever that voltage drop is across the resistor to be across the capacitor. So it's going to be very small. And remember, the capacitor is a short to AC, and this is AC. And I know this, well, not only because I'm an engineer and I've done all this before, because I can hook it up to that there frequency generator and simulate this circuit at a smaller voltage, and that thing won't shut off. It'll allow me to do my testing. I can change the voltage and whatever I want to do. And I run it through a microwave oven transformer to get because you're limited on the voltage on those frequency generators. That one only goes, I think, to 20 volts peak to peak. But if I use a microwave oven transformer and I put the 20 volts in, I get, you know, about 150 to 200 volts out. And I can simulate this whole thing to find out what happens when you try these different scenarios. And you can try it for yourself. You'll see that normally with this open, measuring with just a voltmeter, you get around 150, 200 volts. But once you put a capacitor in there, it runs through it just fine, depending on the frequency you got. You have to tune in the resonant frequency, which is the nice thing about a frequency generator. You can change it to whatever you want. And once you get the resonant frequency here with whatever capacitor you're using, you get the max voltage. Now you drop a resistor across there, and depending on the size of that resistor, if it's a small, your voltage goes down. That's that on there. There's so much I could discuss about this entire circuit. I could make a video that was all day, literally just going through scenarios on this imaginary circuit you got right here. So let's look at the circuit I have here. What I have laid on that table is this here. It's a fairly simple circuit, similar to the one that's over there. However, you can see that the diode is moved. And if you don't put this diode here instead of here, which is after the capacitor, then the NST shuts off. And what I'm doing here is I'm taking the voltage from this NST and I'm charging this capacitor, and it charges in one direction and then discharges back through the transformer when it hits a certain voltage, depending on this gap. Now there's almost an infinite number of situations just with this spark gap, the capacitor, and the voltage being applied to it. So the frequency is not really based off of this, even though this little guy I have over here, which is a 4.5 kilovolt NST, which is just a 12 volt version, which I have plugged into this power supply, it will only put out roughly 2,000 volts is how much I can get out of it with this setup. So I tune this spark gap to the highest voltage I can get out of the NST. Then I can tune the capacitor, which you kind of have to do these at the same time, but then the capacitor here determines the frequency at which that's going to jump at. So the smaller the capacitor, the higher the frequency. The larger the capacitor, the lower the frequency. And then you have the energy that's dropped out of this instantaneously collapses the field here, which induces your power on this side. Now I think this is mostly correct here. Now you're probably saying, well, this circuit is completely different, and you're right, it is. It's totally different. So these two circuits are completely different. Now he kind of has some things in here that I think are redundant. This resistor for one, and this varistor number two. This is going to limit the voltage in your circuit, this also is going to limit the voltage in the circuit, so I don't know why you would do that. One thing I'd like to mention about this entire document, if you've ever downloaded it and read it, and you know, I have the whole thing, you know, here in a spiral notebook. I read it once a long time ago, and then I realized it was garbage. Is that whoever drew this schematic here, I don't know if it was Don or the guy who wrote this book, but the guy who wrote the book is, I'm sorry to say, he's not very smart. I'll just leave it at that. And if he also drew this, then that explains a lot. Now, this circuit over here is limited, it has a voltage limiting by this spark gap. Your capacitor and your diode have to be rated to take whatever NST you put on here, and honestly I think the suitcase device that Don had was probably ran with not a battery operated version of this, but the kind that plugs into the wall is has a higher voltage and a higher power than rating than this guy here. And the reason I think that is because of, you know, he's got earth ground. I'm guessing that's earth ground, and you don't earth ground one of these. It doesn't do anything if you earth ground it, you know. So but it does have an effect on the other ones, you know, and I know I have one of those other ones that is, it's a, you know, it's digital like this one, but it's not the bigger old style. Has a frequency of around 30 kilohertz. This one's frequency I think is around 22 to 25 kilohertz. Anyway, that's why I also think that he used a different NST than is listed in this document. And by the way, you know, if you watch his 98, I think it was, symposium, and he has that suitcase, you know, the other thing that would cause this all to work is a car battery and an inverter. That would be the easiest way to do it. If you're not going to show anybody what's in the case and you're just going to tell them that this is what it is, then you could have anything in there. So let's keep that in mind. However, I do believe this works. I don't know, you know, if Don Smith's ever worked or not. I can tell you that a lot of his ideas are just theory, and he only had one working device. Okay, so now what I have here, here's your neon sign transformer. I got it pegged at this just junction block here, so I don't have to hold any of the wires. I do have a watt meter, which this power supply, actually both these power supplies are plugged into, but I'm only using the top one for this NST. And I got the bottom one for something else I'm going to show you as well. But so there's a watt meter there. I do have earth ground on here, so you can see what happens, and that goes from there to there. And I also have another earth ground which goes to my meter. The high voltage probe requires an earth ground. Then I have, this is the diode that's in the schematic. This is a 20 kilovolt 3 amp diode, and then a 10,000 volt 0.1 microfarad capacitor, which are tied together with the diode here and here. It's just like the schematic. Then I got this transformer. So this transformer, you'll notice, is different than anybody else is using, and except for Don apparently. So what I did is I built one like he had, because if you're going to do an experiment, it has to be as close as possible to what you're doing it against. And so I built this to, as far as I could tell, what he was using. And I actually joined these together in a bifilar kind of style because it works better, and I'll show you the difference there too. By the way, this video is going to be fairly long, so if you don't want to watch it, I don't care. And then on the other side, there's two coils here, and you can see them here. It's 18 gauge there, and then the pairs come off here on this side and are joined together. You can see, if you want to pause it and see how they're joined together, you can, but I'm not really going to explain it. I just have them tied together in parallel, really, and they go to they go to my little tiny load, which is my light bulb. And then of course I have the meter hooked on there, we have this fluke meter here. I'll turn it on. It's on AC, and right now there's, of course, it's off. This is my graphical multimeter. I have a scope, however, I fried it and it's being fixed right now. I was measuring something that was a little higher voltage than I thought it was. It's like 40,000 volts, and I thought it was only like 20. So anyway, that's being fixed. So we'll be able to see the frequency on this. So this is not as good as my scope, obviously. This is just a scope meter. But it'll do. Now the probe is just touching on the spark gap, and that's good enough. You have to multiply whatever you see here by 1,000 because it's 1,000 to 1 probe. So keep that in mind. Then we have our spark gap, which is a titanium spark gap, a very close gap because I've only got 2,000 volts to work with, and then the other side of the NST is connected via this blue wire. But it's easier to look at the schematic because I got it looks like a mess right here. So let's go back to this transformer now that we've seen everything. Where did I see this, right? Well, if you watch Don Smith's 2001 video, he shows the suitcase device, allegedly. Now, if you may not have seen the video, I'm sure you have if you studied Don Smith, but you may not have realized that he showed you the suitcase device. But I happened to print off a picture of it. There's a glare, great. So there it is. There is that transformer right there, and you can see underneath there it's got 2 coils under there wound on there, and then down here they're paired together and connected to that terminal block. That's his output. Over here you can't really tell much where the NST is connected directly to it, which would never work. That's a dead short. And then he has them 2 wires up there like antennas, which I have to wonder if he tied them together. But I did follow those loops of wire, and they are, if you tied those together, nothing would happen. But I've done it both ways, and like I said, I'll show you that. And I have a few more windings on here than he does, just for the primary. And I don't know how many windings he has underneath there. Obviously I can't count them, but that's the device. And this one here shows his NST there. But you have to remember, when you're looking at these types of pictures, or when you're looking at his devices, every one of them actually is a model. It's just a model put on a board. It looks pretty, but that's all it is. It's just a model. It's his theory put on to real life, but it's not working. Most of them are not working. And how do I know this, right? How do I know this? Well, I'm pretty good at reverse engineering things. I was a reverse engineer for a while actually, and I had to decide if somebody was getting their a part warranted or not, and I had to figure out what happened. So usually when you get something to work, you get this one device to work, and for Don it's this device, probably minus that device, and adding a bunch of other crap that you don't see. Then he theorizes, if this works, then I can probably get even more energy if I do X, which would be his other devices you've seen, which involve coils like this, a larger one, a much larger one than this, which I have, and it's in the background here, but and a larger amount of RF, which is what I was working with when I blew out my O-scope, by the way. Those again are just theories. So after all the things that I've studied, that's what I've come to conclude. And I know this because I built things that work, and then I go, I can probably simplify this by just doing X. And of course it doesn't work. It doesn't work because I just theorized it. Now I got to go back through it and figure out why it doesn't work, then make it work. So it takes some time. Anyway, let's have a look at what this circuit does. Now you're going to see some interesting things here. The light bulb's going to light up. It's going to light up past its full brightness, and we'll just have a look at some voltages. So let me go ahead and turn this on. There's our light bulb. A little tiny spark going on right there. Now let's look at this meter here. So you just multiply that by 1,000, and it's not very high actually. It's strange. Sometimes it measures 2,000 volts, and now it's only measuring 200 and some odd volts. But it depends on the capacitor I have here as well, which we will try a different one just for the hell of it. Now over here, this light bulb it's well lit. It's as bright as it should be, and I'll show you how bright it is with actual 12 volts here in a minute. And that's why I got that other power supply over there, so you can actually see what it looks like with 12 volts, and it is much dimmer than that. It's a 12 volt car light bulb, so it's not supposed to be plugged into the wall like the light bulb you see over there. Now this meter here, you're curious to see the voltage on that, right? Well, there it is. It shows 306 millivolts. I have no idea why it shows that for voltage. Now, I assure you this meter works. I plugged it into the wall just to find out, just to make sure, because for whatever reason I cannot measure the voltage that's right here accurately. And I'll switch it to DC just in case you're wondering. Now, I'm not here to fool anybody. I don't care about that at all. But there's no way that's 0.1 volts here. Oh, now we got 1 volt almost here AC, but yeah, that's not the case. So this works really well. Now, I know the other question is this over unity? Well, no, it's not. This is our watt meter right here. When you get in there, you can see it pretty well, I think, from right there. Yeah, just over 41 volts, or watts, 41 watts right there. Now, you're probably curious to how much this guy consumes. Well, we can show you that here in a second too. So you can do the math and you can subtract it. And actually, why don't we do that right now? I'll just turn it off. If I can pull this out of here, we'll try it. Almost got it. I had a tripod and it broke. Okay, so NST unplugged. There's one wire there now. Let's turn it on, see what the watt meter says. If you can see that. So it draws about 5.5 watts or so, just with nothing connected to it. And that's typical. I think this bottom one draws about 6.6. Depends on what's in there. Now, you can do the math, you can subtract that out of there, but however, I couldn't tell you what that thing is drawing, and I'm definitely not going to put my meter in there to measure the current because I don't want to ruin it. I already blew one meter up, and I'm not counting the O-scope. That was a different meter. So it works really well. Now, what I think is missing to make this over unity, I guess, and I don't have the time to do the rest of this, but what I think is there's a capacitor that needs to go in front of this right here after the diode, like this. So you see there's no capacitor. This here. If this was here and it was a resonant tank circuit with whatever frequency you have, then maybe this will work. I don't know. However, what I do know is the voltage that goes here is proportional, of course, to the energy you get out. So this little guy here, not going to power a bank of lights, no way. Why? I just don't have. I got maximum 2 kilovolts right there. Now I have powered this with a larger NST, which is no longer with us, and I can light the 40 watt bulb over there with that one. and it actually draws 25 watts. So when I, over here anyway, that's the watt meters measurement. So there is some more testing to do. I'm not totally debunking this, but I am debunking this. Anyone who sets this up is going to be disappointed. You have to have a little more insight to this. This is an idea, and if you have an electrical background, you can say, well, I kind of know what he's trying to do here, but this isn't going to work. That's not going to work. This is in the wrong place. You know, you just need a little more insight. But if you want, you can take this simple little schematic here and set this up yourself. You can get yourself one of these. Of course, I had to buy the parts and pieces of this and then build it myself. You can order one custom for around $500. But if you just want to scrape by and get into this, get one of these transformers. This is just a normal power supply transformer that's like 110 volts in on the primary and like 24 to 16 volts out on the secondary. That's it. This little guy works pretty good, actually. That's why I have him on the table. But I noticed when I wired this one with the bifilar connection there, it worked better than that one over there. So I decided to use it. And this type of transformer is called an amorphous style transformer. I don't really know exactly what they use them in, you know, in everyday life, but I think it's just a filter. So the next thing is I am going to buy another one of these, a bigger one that plugs into the wall, not a DC version, but and then I will do some more testing with it. But the next thing I was going to say though is this capacitor here, the value of it. The thing that Don says, or whoever this guy wrote this says, is he has a 8,000 microfarads. That just sounds like a huge amount, right? Well, it's not. It's only 0.008 farads. If you ever worked in the car audio industry, you know that they use, you know, 5 farads when they're putting together those stereos. I know I used to do that, actually. You know, 5 farads, not microfarads, but, you know, whole number 5. Huge, right? Well, just to get one that's that big, 0.008 farads, is actually expensive because of the voltage you need on the rating there. Now, that could be this capacitor right here, I believe, is the capacitor that goes right here. Why? How do I believe that, or what makes me say that? Well, I got this handy dandy little app on my phone here, and wow, it's really terrible. It's not in focus very good, huh? What this tells me is if I want 0.008 farads, then I need an inductor that's this size, which this is my inductor actually. That's this guy right here. I measured him with an LCR meter. If you're doing this kind of work, you need to get an LCR meter. It's more accurate than your those types of meters that measure both capacitance and inductance. An LCR meter is designed for that, and it actually you can choose the frequency as well at what you're going to read it at. But BK Precision makes a fairly decent one, and that's what I use. So anyway, back to this. That's the inductance right there, 36.4 microhenries, and the frequency is about that, 294 hertz, and that would allow you to use that capacitor right there. And we're solving for frequency, by the way, on here. And now let me turn this back on, and let's have a whoops, I gotta plug that back in, which isn't gonna be easy with one hand, so I'm gonna kind of set you down here for a second. Okay, we're plugged back in. Let's see if I got it right. Okay, yeah, I got it. Now, the frequency varies a lot. Now I just solved for the frequency over there, but you can see it's fairly close. And yeah, it's 400 hertz right there, but if I change to an inductance like this one, let's say we're going to solve for the frequency on that one, and we wanted to use this number, 0.008 farads, if that is indeed what he was using, which would make sense if he was using this style of this many windings, I should say. It doesn't matter on what transformer, because if you put in that NST's inductance, which is 8.3 henries, so let's change this to henries. Just give me a second here, and then we'll change this to what did I say, 8.3, and I'll show you the numbers here in a second. Okay, the frequency isn't right. Right, that's a very small frequency, right? 0.6 hertz. So it doesn't work. It doesn't work out right. There's no way that's what he's running over there. None of this would work. And this is kind of my method of reverse engineering stuff, is you take the numbers that are given to you, you measure what you know is available to you, and what you see him make, and then you plug those into your calculator, and you see what happens. And if the numbers don't line up, well, then you got to make them line up. You got to assume that, you know, he's trying to throw you off because of whatever contracts he had by not showing the capacitor here at all, putting the diode in the wrong place. Just move it over here. The varistor is just a spark gap, you know, or this is the spark gap here. I don't know. This actually won't work. You just get rid of that altogether. So there's a lot of variables here, and if this is right, 0.008 farads, then he had it across here. Now I don't know what's going to happen when you put this into resonance. What is going to happen to the voltage? There's a maximum voltage that it will reach, and depending on what that frequency in the resonance is, that it could be a higher or lower voltage than I already have right here. So that's something I need to test. I don't have this capacitor. I could order it, and it's a large capacitor, because I'd get one that was at least, I don't know, 10,000 volts, because I plan on using a larger NST because I want more power out, and I know that I need a higher voltage to do that. So there's no way this little guy lit up all those 100-watt bulbs at his 98 Symposium or whatever it was called. It had to be the larger one, plugged into an inverter that was plugged into a battery. There's just no way that's going to work, first of all. So don't buy one of these. Don't waste your money. Go ahead and get one of the larger ones rated at 10,000 volts. That's what you're going to need. 10,000 volts, plugs directly into the wall. And you can buy an inverter and a battery if you want, but I just plug it into the wall until you figure some stuff out. And then you're going to need to, whatever inductor you have here, you're going to have to measure it with your inductance meter, your LCR meter, and then find the right capacitor for you that's going to go across here. Will that work? I don't know. I have no idea if that's going to work. I have dropped the capacitor across that just to see what happens. A random one, mind you, and the light bulb gets dimmer, a lot dimmer. So I don't have even close to that capacitance. So can't do it. And I don't know if I will or not, honestly, because I travel a lot. I'm going to be gone until December after this trip, so if anybody else wants to see something, they'll have to contact me directly for one, because I don't allow anybody to leave comments on my stuff. But I'm going to cut away for a second. I'm going to show you that light bulb plugged into a 12-volt power supply, and then I will also hook the meter to it so you know that I am not lying when I lie. So I'll be right back. Okay, back again. Got it plugged into the bottom one there. I left this lead disconnected so that we could have a look at the watt meter, and without the light bulb on. So there it is, turned on. There is how many watts that power supply draws just with no load. Could be that switch there. I don't know. I don't think that's 6 watts, but who knows? Let's plug in the light. Light is now on. That's kind of hard to get an angle on there with the cameras glaring, but you can rewind the video and look at how bright it was over on the table over there. But there it is, lit up with 13 volts. Here is that voltage, 13.12 volts, and here is the watt meter. There's a little bit of a glare, 17 and a half. So there you go. You can say this thing's drawn about 10 watts or so, I guess. And now you know, light bulb is a lot dimmer than it is over there. And if I had my oscilloscope, I could measure the voltage on this while it was plugged into that transformer. I think what's happening is the frequency coming out of the end of that is just it's just too much for this guy right here. So anyway, I'll set this back up and I'll show you what happens when we mess around with the earth ground, and we will change this capacitor, which is the 0.1 microfarad capacitor, to this capacitor, which is 0.01 microfarad capacitor. Okay, so I'll set that up and be right back. Okay, I'm back. I know, it seemed like forever, right? Okay, so light bulb on, burning really bright. Now I changed this capacitor like I said I was going to do, and this has got a higher pitch squeal now, and here's our reading on the meter, and you can see now it's at 5.2 kilohertz ish, and almost 2,000 volts, so 1.9 times 1,000, remember, about 2,000 volts. Now what's odd now on this meter, since I changed that capacitance, it's now reading 14 volts AC. Okay, AC. It's strange how that is. I know the frequency somehow messing with it. I can change this meter here to a different screen. You can see the pulse on that. Anyway, that's what happens there with the different capacitor. I could change that down to a smaller capacitance. That's even 10 times less than that one. It's like 0.001, but it's so small that you don't get much out of there. Frequency goes way up, but so this is the earth ground. I'm just going to pull it off if I can without getting zapped. So I took it off. Light still looks the same to me. Actually, the voltage is now 16 volts. However, now this meter doesn't look that clean. It sounds like it might just quit working. But you can see now we're almost at 3,000 volts without the earth ground on there. Now I'm going to touch it on there while I have the camera held here. I touched it. Oh, it cleaned it right up. That's pretty interesting. It's like it filters out the crap through the earth ground, and when you take the earth ground off, the reason the voltage looks so high, see it's off, is because of the noise that's actually on there, and it's harder to tell what the meter anyway doesn't know where the average is now. But I put the earth ground back on. Cleans it right up. I wish I had my oscilloscope. I would like to see this one actually. I could switch these meters around, I suppose. And the light bulb got a little bit dimmer due to what's going on over here. It fluctuates. It's more stable with the a larger capacitor on here. So now I'm going to take this wire off here and hook this up how you see in that picture, and we'll leave this capacitor for now, might as well. So let's do that. And we're back again. So all I did is I just untied those two together and connected the main power across the two ends there, so it's not connected in bifilar anymore. Now the light bulb is very dim. It's probably the same as it is when it's connected to the 12 volt power supply. And here's what this meter says the voltage is. Now you can see when it squeals really loud it goes up actually, which is interesting. And here's what you see over here. So we got 1500, 1600 volts at 10-ish kilohertz, so it keeps jumping around. Anyway, light bulb, pretty dim. So let's reconnect the other capacitor in there with the same situation. We're back and I have it turned on, and all I did is I swapped out that capacitor. You can hear the difference there. Let's see what's going on over here. It looks like we have a lower voltage, 283 volts at a lot lower frequency. Over here though, light it's brighter actually. It looks almost as bright as it would be with these two wires connected. Here's an interesting thing I noticed. I'm going to take one of these leads off of here that I'm measuring the light bulb with. Now look at the meter. It says 30 volts. Now I'm going to touch my finger on the end of that lead. 108 volts. Interesting. And all I did was just touch the end of it like that, while the other end is connected there. Now if I touch this lead to earth ground, it goes, I think it goes even higher. So I'm going to do that. There's earth ground, 170 volts. It's pretty interesting that it does that. It doesn't zap you, and I don't know if that energy is usable. But it's pretty high. And I often wonder if somehow this side of the circuit should feed back to this side of the circuit, causing an oscillation back and forth, which would amplify your input, but I'm not sure how that would be set up. But nevertheless, that is pretty interesting that you can take that off there and the voltage actually goes up, and when you touch it, it goes even higher, and then when you connect it to earth ground, it's even higher. And I have tried connecting that light bulb between one lead there and earth ground. It doesn't do anything, just so you know. But anyway, I'm going to reconnect that back to the way it was, and we'll just have one last look. And we're back again, and so we just connected that lead back on there, and I'll throw the switch. The light actually looks similar to me that it did before, and we are not reading anything over here again, and that is because I got that other capacitor in there. It just goes ape shit. If you can see that, it's in the millivolt range. Yeah, it's like there's no way this is in the millivolt, you know. And I'm connected across the light bulb. Here's our other meter. Looks like we're still around 300 volts, 283 volts, and there's our frequency at 400 hertz. And let's disconnect the earth ground on this one too. I don't know if we did that on this one. Oh, just quit. So the earth ground seems to stabilize things, is what it does. I think we'll just leave it at that. So there's so much theory that I could go into behind this. There's so much more I could talk about, and I know you're like, damn, you talked a lot and you won't shut up. But there's the two little circuits there. You can take a screenshot of that and just build it if you want. You don't have to use this style transformer. I do, because it's what he had. Like I said, use one of those for building power supplies with. Just your load connects to this side. those who have no electronics background, the primary side is always the skinny wires, remember. Well, depending on what kind of transformer you've got. If you have any questions about this, you can contact me through YouTube directly. The comments are always turned off on my videos, so you can ask questions and things like that. I'll do my best to answer. I travel a lot for my current job, and I think that about covers everything I wanted to share. So if you are feeling generous and you want to donate this capacitor to me to further this experiment, you can look on the internet for something as close as you can get to this value, 0.008 farad or 8 millifarad, however you want to, whatever you want to call it. You can even call it 8,000, I don't care, just look it up. You may have to special order it from a company in China, which is how I get a lot of parts generally. Have them custom made, and just make sure it's rated at a minimum of 10,000 volts. I prefer 15 to 20, but that's going to be a lot, and it's going to be a very big capacitor. You can see that capacitor over there is a 90 microfarads, and it's not that big. It's like the size of a Rockstar can. So one that's, and that's only rated at 400 volts too, so one that's rated at 15,000 and is closer to a whole number, 1 farad, then that one is just going to be enormous. So if there's anything you want me to test, just send the parts to me, and if you are serious about it, I will give you my address and you can just ship them to me. People do it all the time, and I'm pretty good at reverse engineering things and thinking how they think when I look at their stuff, their schematics. So that would help out a lot. Then maybe I could have that capacitor by the time I come back, and I will put it in there and see what happens. Anyway, hope this answers a lot of questions for you, Mark, and for Frank, who really wanted me to post the schematic on what I was doing. Now that's done. If I find anything else out, I'll keep you posted. So thanks for watching, if you could stand watching the whole thing.